Okay, so let's continue this lecture series by talking about quantum numbers. We've discussed quantum numbers very briefly in the previous lecture, and that was the principal quantum number, or the energy levels of the electron orbitals, right? That kind of matched up with the Bohr model and gave you the most probable location of an electron, right? Well, what exactly are quantum numbers then? What exactly are quantum numbers? Well, when we use the wave equation to solve for the wave function, what it gives us is, the energy of orbitals, right? It gives us the energies of the orbitals. And so those energies of the orbitals, right, and their orbitals, they can be described by a set of, these orbitals can be described by a set of three quantum numbers, right? And one of them we already discussed, which was the n principal quantum number, right? So that's n. There's also two others. There's one that's called L, and there's another one that's called M. M can actually be broken up into M sub S and M sub L, but we'll talk about those when we get there, right? But so there are three different quantum numbers. So now let's go through and talk about each one of them in detail. So what is a principal quantum number, n? Again, n, it describes the energy level, right, of what each orbital resides. And so we saw this already before when I drew you the hydrogen atom, right? And there's the one proton there, and then one electron for hydrogen atom. If hydrogen had more electrons, which it doesn't, right? There's another orbital there, and there's another orbital there, right? And you just can keep on going on for however many you need to fill up for whatever element you're doing. But we're using hydrogen right now. And so the very first orbital is n equals 1, right? That's the ground state orbital. And then the second one is n equals 2. And the third one is n equals 3, and then so on, right? And so the further away you get from the nucleus, the higher the principal quantum number gets. And I say usually, they actually are always whole numbers, right? And so here it states right there, the value of quantum numbers are always greater than or equal to 1, right? You'll never have a quantum number that's 0 or negative, because they just get bigger as you move away from the nucleus of the atom, right? And of course, these numbers, they actually correspond to the same energy levels that are on the Bohr model, right? So the next one is called the angular quantum momentum quantum number, and that's L, right? And so L, the short story of it is that the L actually tells you what the shape of an electron orbital is, right? Not the actual orbit like around the atom, but what shape that orbit is. Okay, and so for values of L, you can be anything from 1, 0 to 1, 2, or 3, right? And so if you have a value of L that's 0, then you have what we know as the s orbital, right? Which is basically a sphere, right? So if you were to put an atom onto like a three-dimensional graph, like so, the s orbital would be a sphere right in the middle, right? If you have an L that's equal to 1, that's going to be the p orbitals, right? And the p orbitals are usually these things that look like hourglasses, right? Those are the p orbitals, and they can, and I'll have better pictures of these later, but they can be on any axis, the y-axis, the z-axis, or the x-axis. And then we have the d orbitals, right? And the d orbitals actually have a L quantum number of 2, right? And so these guys are also the shape of hourglasses, except there's 4 lobes to them, right? And so they're 4 lobes, except for one. One of them has a donut around it, but it's only one. And you'll see that one in a second. But most of the d orbitals are like clover shaped, or they kind of look like the highway whenever you do the clover shaped entrance ramp or exit ramp on a highway. That's what they kind of look like, right? And then F, that's when you have F orbitals, and they have a L quantum number of 3, right? So you have an angular momentum quantum number of 3. You have the F orbitals, and I'll tell you now that the F orbitals are too hard to draw, and so I'm not going to draw for you. I'll show you pictures of them in a minute. Okay, so that's what the L quantum number is, right? So quick review: N quantum number tells you what the energy level is, right? What level the order is. So is it N equals 1, which is the closest one? Is it N equals 2 to the next one, or whatever? Whereas the L or the angular momentum quantum number tells you the shape of the actual orbital, where the electrons actually are floating around and residing. The shape, not the actual location. Okay. And then we have, like I said before, there's the magnetic quantum number, which is m. The first m we'll talk about is the m sub l, right? And so the m sub l actually tells you, well, its definition says the magnetic quantum number describes a three-dimensional orientation over the orbital, right? And so if the previous one, which was L, told you the shape over the orbital, M sub L tells you what direction it's moving, what direction its position is, right? What its orientation is. It up and down, or is it left to right? Is it diagonal, something like that, right? And that's what M sub L is, right? And so what's interesting here is that M sub L, right here, can be anything that is minus L, right? That is minus L less than or equal to M sub L, which is also less than or equal to L. And so what does that mean? What does it actually mean? Well, it means that, for example, we know that there's only one s orbital, right? That's that sphere. That sphere I showed you a second ago, right? That's the s orbital. And you'll see a better picture of it later in a second, right? Well, if L is, we'll go back and look at the values of L, right? So if L is 0, right there, right? L is 0 because the s orbital is 0, right? If L is 0, and we plug in 0 here, right? And we plug in 0 there, right? So what it's going to say 0 like that, and then ML, right? M sub L, and then less than or equal to 0. And so what that means is, what is the only value that fits in that equation? What is the only value that will fit in there and be true, right? Well, that value is 0. So M sub L, all it has in it, it's 0, which there's only one of those digits there, right? There's only one orientation right there, okay? That 0 is that single orientation. And so what that tells you is that there's only one s orbital, which makes sense because the thing is a sphere, right? No matter how you orientate it, it's always going to look the same. So there's only one orientation for a sphere, okay? So let's try this again now. We'll try it again now where we look at the p orbitals, right? The p orbitals right here, right there, right? What is its L value? Its L value is 1, right? Does that make sense so far? And if its L value is 1, let's try this again now. This time we'll do it with the p orbital, right? This is the p orbital, right? I don't want to get the poor orbital. Let's just write it down here, right? So for the p orbital, right? Remember this. So this is the way we determine what m sub L is, right? And so if the p orbital only has the an L of 1, of L equals 1, and we plug in that 1 here, so we say 1 negative 1 is less than or equal to m sub 1, which is less than or equal to 1, right? What are the possible values of m sub 1 then, or m sub L then, right? Well, we already know 0 will fit there because 0 fits between negative 1 and 1, right? So m sub L is definitely 0. Oopsies. 0, right? But then it also says equal to, right? And so you can actually add in negative 1 there too. And then you can also add in 1 there too, because 1 is also equal, right? And so what that says then is that there are 3 orientations for the p orbital, right? There are 3 orientations for the p orbital because there are 3 digits here. 1, 2, 3. And that's why we get right here, there are 3 p orbitals, right? Oh, I'm sorry, I blocked my thing. Let me move my fat head out the way so you can see what I wrote there, right? Oop, that's not right. There it goes, right? And so you can see here that when you make m sub L, right, when you plug in negative 1 and 1 there for the m sub L equality there, right, or less than and equal to there, there's 3 positions, right? There's 1, negative 1, 0, and 1. So there's 3 positions, which means there are 3 different p orbitals, right? Let's try it for the d orbitals now, right? So d orbitals is 2, right? So if you have a d orbital, right, your L number is 2, right? And so let's try this. We do negative 2 less than or equal to m sub L less than or equal to 2, right? And so what could be the possible values for m sub L then, right? Well, we know that 2 fits because it's greater than or equal, it's less than or equal to, right? So negative 2 is definitely there. What's between that and 0? Negative 1. Then, of course, 0 is between negative 2 and 2. And then 1 is between negative 2 and 2. And then 2 is equal to, right? And so here we have 1, 2, 3, 4, 5 positions, which means that what that means then is that you have 5 d orbitals, right? 5 d orbitals, right? Because you have 5 different orientations they can be at. Let's see if I'm right. Yes, it says right there 5 d orbitals, right? It says 5 d orbitals. And you'll see what I'm talking about when I say d orbitals in a second, because they're all just basically the same shape, but just in different positions, right? And then the last one is the f orbitals. It says 7 there, right? Well, that kind of makes sense too, because if you put in the equation, for f orbitals, right, it's actually the L number is 3, right? And so let's just try that real quick, right? Well, so that means negative 3 less than or equal to m sub L, and then less than or equal to 3. So we'll write all of the numbers that are true here. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. Oops, I accidentally wrote a 5 there, but you know what I mean. 3. There we go, 3, right? How many digits are there? 1, 2, 3, 2, 3, 4, 5, 6, 7, right? So there's 7 possibilities for F orbital, right? Which means that if you go forward, oopsies, sorry, where am I at here? There we go. That means if you go forward there, you see there are 7 F orbitals, right? So you can see how the m sub L actually just predicts for you how many different types of orbitals within how many different types of s orbitals, how many different types of p orbitals, and how many different types of d orbitals, and how many different types of f orbitals, right? You can have just based on the angular momentum quantum number. Okay, so that's what that means. So this is just a little chart here that kind of summarizes everything for you, right? So if you have an n of 1, right, that's an s orbital, right? Because a principal quantum number of 1 means that you're at the lowest energy level, number 1, but then also that the possible values of L there are only 0, which means if you have a 0 there, that means that you have an s orbital, right? There's only one possibility for an s orbital because it's a sphere, right? That's the m sub L, and then the number of orbital subshells. There's only one, and then there's a number of orbitals in the shell itself. There's only one because it's just the sphere, right? No matter what orientation you put it in, it will always be the same orientation because it's a sphere. Okay. Let's keep on going for a couple of these here, right? We have then an n equals 2. Again, that goes up to your second energy level. But then the possible values of L that you can have for an n equals 2 is 0 or 1, right? And so that's the 2s orbital and the 2p orbital, right? And so we already know that when we have an s orbital, there's only one possibility for L, right, and one subshell, right, or one shape, okay? But here's the p orbital, right, because an L value of 1 means you have a p orbital. P orbitals have 1, 2, and 3 possibilities for shapes, and so that's why it shows 3 there, right? And then we can just do if you go up to 3, you have 2 down there, right? So D has 1, 2, 3, 4, 5, right? And so that's why it says there's 5 shapes for D. And then for the third one, which is F, has 7 of these here, and so that's why there's 7 different subshells, because there's seven different shapes of the F orbitals. I just want to reiterate again that the F orbitals are really difficult to draw, and we don't ever study anything in the F orbitals, so don't worry about that too much. So these are the shape of the s orbitals, right? The s orbitals are spheres. They're literally spheres. So the L is a 0, right? Because no matter what orientation you put it in, it's always going to be it's always going to have just one shape, right? It's just going to have just one shape. It's always going to be a sphere, okay? And then the sphere's value increases, right? The radius of the sphere, right, will increase with the value of n. So as your energy level goes up, the value of n goes up as well, right? Or let me say that again. If the value of n goes up, the sphere's size also goes up too. The radius increases too, which makes sense, right? And I don't have my face showing right now, but I'm doing all these hand gestures to kind of help you. But you know what I'm saying, right? So this is an n equals 1. This right here is n equals 1, so that's the smallest s orbital. This is n equals 2, the next smallest, the next smallest, right? Or the next largest, the one that's right after that. And then this one here is n equals 3. Oh, and by the way, when we say, and I mentioned this in the lecture a lot, but like, this 1 here, this 2 here, and this 3 here, those are the n quantum numbers, the principal quantum numbers, right? And they actually help you a lot because if you didn't know this already, which you should already know because I talked about it a lot, but if you have the periodic table, right, this is just a very rough sketch of the periodic table here. Very rough sketch, sorry. All right, so that's sort of the periodic table, I think. Yeah, that's it right there, right? So everything right here, right, all this stuff right here, this is known as the S block, all right? Okay. And then everything over here, which are the nonmetals right here, and some of them under the stir step too, this is all known as the P block. Right? If you're noticing a pattern, that pattern is that the periodic table is organized so that the electron configuration of an atom corresponds to the block that it's in, right? And so this right here is the D block. Right, and then we also have down here the lanthanide and the actinides, which is the F block. And I don't ever study any F block atoms, so don't ask me any questions about F block atoms. So that's the one thing to notice, right? And then the other thing to notice, right, is that when you have the periodic table, I'm just going to draw another very rudimentary periodic table right here, right? You know how there are rows like this, right? Well, we already know what columns mean, right? Columns tell you I don't have enough columns, but it's because it's too small. But you know what I'm trying to do here, right? The columns tell you the number of valence electrons, right? The column number or the group number tells you the number of valence electrons. We talked about that ad nauseum, right? But then the row numbers, right here, are also known as the period numbers, right? They tell you rows or periods. If I could actually write it out, right? Or periods, right? They tell you the n number, right? The n equals number. So things that are on the first row here, that's n equals 1. The second row is n equals 2. The third row is n equals 3, right? And so on, right? Until you get down to the bottom of the periodic table. So when you look at what we're getting to pretty soon is electron configuration, right? When you look at something that looks like this right here, right, that 1 right there tells you it's in the first row, right? And so that's n equals 1. And this S here tells you it's in the S block, right? Whatever atom this might be, okay? And so actually this has to be either a hydrogen or a helium because only hydrogen and helium are in the first row. So that has to be what that is. But anyway, 2s, right? That means second row in the S block, 3s, third row in the S block, right? So this is probably a sodium or a, okay, I'm going to embarrass myself because I can't remember what comes after sodium. No, lithium, it's lithium. Lithium or beryllium, right? So the 2s ones are probably a lithium or a beryllium because that's what's in the second row. And then in the third row, dang, what's in that? That's sodium and calcium, maybe? Dang, I can't remember what the next one is. See, back in the day, they made you memorize the periodic table. But anyway, you can really narrow down the periodic table what the element is just by knowing its configuration, its electron configuration. So remember we were talking about how the wave function can kind of predict where an electron is possibly at most likely, right? And so here is an example of the kind of like a curve that you would get from solving the wave function. And wherever the peak is the highest, right, is where the electron is most likely to be. That's the most probable place that an electron will be, right? And so at the 1s orbital right here, right, you see how that 1s, the border of that 1s orbital sphere right there matches up to the where this peak is, right? And what that peak is that on the x-axis, this is the distance from the nucleus, right? So again, when Bohr figured this out with his Bohr model, he used the energy, but now we can use the distances with the wave function, and they actually match up because of the energy, right? 2s orbital, a little bit bigger, right? And so now we have two locations where electrons can be at those two peaks, right? About the first one, of course, is still 0.05, like this one was 0.05, but the second one now is about 3 angstroms away from the nucleus, right? And then if we have an 3s orbital, then 0.5, and then I said 3 there, but I guess it's more like 2.5. But yeah, about 2.5, and then the 3s orbital is going to be at the 7, right? So these waves, right, give us these distributions, and these distributions tell us where the electron is most probably going to be, and that dictates how big the s orbital is, right? Whether it be the 1s orbital, the 2s orbital, or the 3s orbital. Okay. So here are the p orbitals, right? I told you a few minutes ago that the p orbital looks like an hourglass, and there are 3 different p orbitals: the pz, px, and the py. And the reason why they're named this is because of where they're positioned on the x, y, and z axis. So this is a 3-dimensional axis, of course, and the z axis is the one that goes up and down. And so this is called the pz orbital because it aligns itself with the z axis. And then the px orbital aligns itself with the x-axis, and the y-axis here has its p orbital on it. So the p orbital for the py orbital, right, actually aligns itself with the y-axis, right? And notice how many there are here. How many are there? There's p, z, px, py. Some people do this alphabetically and say px, y, z. Well, that's what I like to do. It doesn't matter as long as you know which is which, right? But notice there are 3 total, right? 3 types of p orbitals, or shapes, not shapes, orientations, right? And then why is that important? That's important because remember just a few slides ago, we did the m sub l prediction, right? Right here, the m sub l prediction. And here's our one for the p orbital, right here. I should write that, p orbital, right? And when we did the one for the p orbital, we saw there are the 3 different orientations right here, right? 3 different p orbitals, and also 3 different p orbitals there, right? And so that's why it's kind of cool that we are able to see what these shapes look like now and why there's only 3, and that's because there's only 3 real axes, right? And so that's why we have the px, py, pz orbitals, and it matches up with our m sub l prediction. So then what that means then is you can see that when we get to the d orbitals, they'll match that too, right? The d orbitals is going to have 5, just like we calculated, and then the f orbital will have 7, right? So let's go on to the d orbitals. These are the d orbitals. See how they look like hourglasses too, but there's just, you know, there's just 4 of them now instead of 2 of them, right? And instead of being aligned with the axes, like these guys are, these are aligned with the axes, aligned with axes, axes, what's the plural of axis? Whatever, axes, what are you I'm saying? These are, I'm Asian, so I'm hard English, I guess. But yeah, these are all aligned with the axes. Whereas for the d orbitals, they're all aligned with the planes. Aligned with the planes, right? So here we have the dxyz, and it's dxyz because it's in the the yz plane, right? Oh, sorry, I said dxyz. Sorry, that says dyz, right? So very small. That's the yz, right? The dyz, and it's called the dyz because the orbitals are in the they're in the zy plane. Here's the dxz. That's because it is in the xz plane, right? And then we have the dxy, which is in the xy plane. And then these other two ones are a little bit different because these ones are definitely that's aligned, all right, to the axis. So it's a little bit different, and so that's why the equation is a little bit different, right? It's like dx squared minus y squared, and then the one real standout here is that it's no longer a clover shape, but it's got this donut right here, and so this is the dz squared orbital, right? That's a dz squared orbital. So if I ever ask you a question, which d orbitals are aligned in the planes, right? Aligned with the planes, then it would be the dx, the dyz, the dxz, and then the dxy, right? This one right here, the dx squared minus y squared, it technically is aligned with the plane, but really we would say that's aligned with axes more because it's aligned with the x-axis and the y-axis. So I would say that these are the ones that actually are aligned with the planes, right? And then the last one here. Also forgot. There are definitely 5 d orbitals, right? So you count there are 5 d orbital types, and then we go back to our calculation right here, right? Oops, I did that on the previous slide, and here we go. So these 5 d orbitals, right? Because 1, 2, 3, 4, 5. When you put the -2 and 2 in for its angular momentum quantum number. And then the last one is the f orbitals, which are really complicated. I don't even want to explain those, right? But yes, they're very complicated shapes, and there are 7 of those. Okay, and like I said, I never studied the f orbitals. I'll never ask you about f orbitals, but that's what it is. Okay. So I told you before how a lot of the energy kind of equation and wave function stuff has been a very difficult process to calculate, and that we've only really calculated one circumstance, which is the hydrogen atom, and we've not done any other ones. Well, yes, that is still true here, right? And then so this is basically we're going to talk about the energy to orbital diagrams for all these different atoms, but they're all based on the hydrogen atom, right? Because all the other ones are very different, or slightly different even, or even a lot different, but they're not exactly the same as hydrogen. But the only way we can actually do this is using the hydrogen atom, because that's the only one that we've been able to solve. And so we kind of use the hydrogen atom as a template for the other energy orbital diagrams of all the other atoms, right? So the first word here to understand is the word degenerate. The word degenerate means that they are on the same energy. Same energy. Right? So for example, when you have the 3 p orbitals, remember you have the p, x, p, y, and p, z orbitals. Those are all degenerate energy levels, or energy orbitals, because they are all the same type of orbital, p orbital. So the only difference is that they are in different orientations, but they're all the same shape, so they all contain the same energy. So orbitals that have the same energy, right, are called degenerate. Okay. So for example, then again, all the d orbitals, right, for one subshell or one shell, like the 3s orbital, the 3d orbitals, right, or the 4d orbitals, or whatever. I guess I can do 3d because there's 3d right there, right? Those are all degenerate as well, right? Because there's 5 of those, okay, and then of course the 7 of the f. So just know that a degenerate orbital is just an orbital that has the same energy as the ones next to it. Okay, those are all the same energy level. And it says it right there too. And then so this is a more accurately spread out energy level diagram right here, right? And so you can see how that the 1s orbital is the lowest of all energies, right? And so if you were to have a hydrogen atom with its single electron, it would just have one little electron right there, right? If you had a helium, it would have 2 electrons because helium has 2 electrons, and it would fill up right there, right? And so now you have a full 1s orbital, right? And then you can just keep on going with the rest of the periodic table, right? So what comes after helium? I think it's lithium. Lithium can go here, right, and put another electron right there, right? And then because lithium has 3 electrons, beryllium has 4, so the next one that goes there, right? And then one after that, which is interesting enough, is boron, right? And boron just goes up like this, right? And you just keep on going until you get to the end of the periodic table, right? And so this energy diagram can go for a long time, but I think what I need you to notice here is that as I fill up these orbitals, I always start with the lowest one first, right? And then I always fill up the I go across degenerate energy levels at first to maximize uh, the space for an electron, and then I'll come back, right? So the one after boron here, right? If I had one after boron, and oh dang, what's after boron? Is it nitrogen? No, that's nitrogen's 5. Oh, what's 4? Carbon. Ha. So carbon is after boron, right? And so if I put one extra electron for carbon in, right, I'm not going to put it here, right, because what you have to do is you have to maximize the area for electrons. And so I would actually fill in the next orbital first, and then that would be carbon, right? And say if I was filling up, oh, and the other thing to notice too is that once I fill them up, you notice here I actually have to have opposite spins, right? That's the m sub s. We'll talk about that in a second, but you can never put 2 electrons in that have the same arrow, like both of them going up or both of them going down. They always have to go opposite directions. So what's after carbon is nitrogen, so I can do one extra one there for nitrogen, right? And then what's after nitrogen? So nitrogen was 5, so 6. Oxygen is 6, right? And so now you notice how I've filled up these degenerate energy levels right here. These are all degenerate, by the way. Degenerate, right? Those are all degenerate, they're the same. So if you have degenerate energy levels, you have to go fill across all these first before you can come back again to fill the rest, because each orbital can hold 2 electrons. And so now I'm done with nitrogen and it's all nice and full, but then I will, like if I want to do oxygen, right, I would fill all these up the same way again, but then I would give one extra electron, and I wouldn't go to 3s, I would actually just go back here to, I didn't mean to draw it so big. It should fit inside the box. One electron going downwards. So the key here is to fill in all of the degenerate orbitals with 1 electron first, and then come back and then start to fill in the rest, right? And then always start at the bottom, going up, and then always make sure that your electrons are always in a different direction, up and down, not up and not down. Okay. So this is the m sub s thing I was just talking about, right? Electrons are just like magnets, and so they have magnets have a north pole and a south pole, and inside of a single orbital, right, you can't have the same spin, right? So here's an orbital right here, right? Just pretend that's some orbital. You can never have an electron that are both of them are pointing up. That's bad, right? You can never have an electron where both of them are pointing down. That's also bad, right? When you fill up the orbitals, you should always have them in opposite spins, right? And so mathematically, that's represented with a plus 1/2, and that's the one that's going upwards, right? That's a plus 1/2, and then if it's going downwards, it's a minus 1/2, right? So you just cannot have so what it means is that, another way of saying this too is that you can never have the same m sub s in a single orbital, which means that one of those sub s's in m sub s's in a single orbital has to be plus 1/2, and the other one has to be minus 1/2, right? You can't have the same thing. They have to be opposite each other. Okay. So all these rules I've been saying, just as we go through this, are the different rules that are set for correctly filling up orbital diagrams, and they all come from actual rules, right? So one of them is the Pauli exclusion rule, right? And the Pauli exclusion rule says right here, no 2 electrons in the same atom can have the same set of 4 quantum numbers, right? And so what that means then is that no electrons can have the same n, l, m sub l or m sub s. Okay, they all, at least one has to be different, right? And so that means that it can't be in the same. If they're in the same orbital, they have to be opposite numbers, right? And that kind of thing, right? So no two electrons in an atom can have the same exact energy, because remember that the orbitals actually just represent like energies, right? They represent energy levels, right? And so no two electrons can have the exact same energy, right? And so that's what the Pauli exclusion principle says. And as long as you're filling it up the way I told you to fill it up, right? The first one is always, start with the lowest. All right, start with the lowest orbital first. I'm going to bring myself back so you can see that I'm actually still here talking to you. There we go. Start with the lowest energy level first. Right, start with the lowest energy level first. And then number two is that, make sure the electrons have opposite spin. That means that one should go up and one should always go down, right? And the third one is that fill degenerate orbitals one at a time first, right, before going back to fill a second electron. So as long as you follow those three rules, basically, you'll always be in compliance to the Pauli exclusion principle, right? Because my three rules actually include the Pauli exclusion principle, also the Hund's rule, which I think we're going to get to in a second, and also the off-bow principle. I never spell off-bow right. Off-bow principle. Shit, I don't even know how to spell principle. Principle. There we go. Whatever. However you spell principle. Right? So now let's talk about electron configuration. Okay. And so what is electron configuration? The electron configuration is how we distribute electrons in the orbitals of atoms, right? And so the lowest possible is of course called the ground state. We've talked about that before. And so we have three parts of an electron configuration here, right? Well, electron configurations get very long, but it's just a series of these guys. And so the first thing to note here, that 4 there is the n equals number, right? And so that's a principal quantum number. And this tells you the energy level. Right? P, of course, tells you the orbital shape. Orbital shape. And then 5 here tells you the number of electrons in that orbital. Number of electrons. Let's see here. Number of electrons present in the orbital. Okay, and so that tells you how many. Like I said, the number of electrons present in the orbital. So let's talk about doing electron configuration then. Oh, I didn't even realize that that I had them actually typed out already right here. So here it goes. Number energy level, right? Number 4 right there. The 4 is the energy level. The type of orbital or the shape is that one right there, P, and then the number of electrons present in the orbital, right there. Sorry, didn't realize that I had already typed that out for you. So like I was saying before, right, in the orbital diagrams, uh, you start out at the lowest energy level, which is the 1s, and you fill those first, right? And then when you fill them, you just got to make sure that they're opposite spin. And then once you fill them up, because only 2 electrons can fit in one orbital, you can move on to the next one, which is a 2s, and put a 1 in there, right? And now you're done with that particular one right there, right? So remember just to follow the rules, right? Follow the rules from the previous slide. So here we can actually take a look at it's kind of small, sorry about that, but here are the electron orbital diagrams, right, for a series of atoms. We have lithium here. And so here's carbon right here, right? There's the 2s orbital, right? 1s orbital, 2s orbital. And notice how we are actually filling in right here the degenerate energy orbitals one at a time first before we go and then add in a second electron, right? And so the first time, I guess they skipped from nitrogen to, that's kind of sad. They skipped oxygen and fluorine and all those, but that's okay. So notice how we fill up all these first, right? Those 3 p orbitals first, one at a time, before we come back and start filling in the p orbitals with 2, right? And so the thing I want you to notice here is that this is the electron configuration right here for lithium, right? And so you notice it says 1s2 and then 2s1. And so what does that mean? That means that in the 1s orbital there are 2 electrons, right? 1s, right? 2 electrons, right there, 2 electrons. Next thing, right, it says 2s orbitals. So it says, oh, sorry about that. It says 2s right there, which means we're at the 2s orbital right here. And how many electrons are in the 2s orbital? Well, there's only 1. So that's why the electron configuration for lithium then is 1s2, 2s1, right? And you can do this with the rest of the periodic table of the elements, right? And of course, when you get to the big elements, the electron configurations get really long, but I'll show you how to condense them later, okay? Because you'll notice that the electron configurations of every single element, right, or atom will be the same as its previous one, except it has 1 extra, right? And so, for example, here, which is beryllium, right? 2s, 1s, right, is full with 2 electrons, and then 2s is full with 2 electrons. So notice right here, its electron configuration is 1s2, 2s2. Same thing as lithium's, except it has 1 extra electron, so that's why it's 2s2 instead of 2s1, right? Boron, right? Same thing again right here. We have a full 1s2, that's right, 1s2. Then we have a full 2s, so 2s2. And then in the p orbitals now, wow, there's a change. Here's our p orbitals. Boron has a single electron right there in the p orbital, so that's why you have to draw it right in there, 2p1, right? Because it's the 2p orbital, right? There's no 1p orbital, so skip that for that. It's always going to start with a 2p orbital. And you know this from the product table, because the product table starts with the p orbitals at the second row, right? And so you can see how you go through the rest of these electron configurations, that they literally are, as you move forward through all the elements of the periodic table, the electron configurations are all the same. They just add 1 more electron into the next, they keep on just adding 1 more electron as they keep on going across the periodic table, and then they start to fill and occupy the appropriate orbitals to accommodate those electrons. So there's this thing called the condensed electron configuration. And the condensed electron configuration was developed because, as I said, when you get to the larger atoms that have, for example, 100 electrons, you don't want to have to go through and write out like 50-something, 60-something, electron configurations. So the condensed one usually is so the condensed one uses the previous noble gases electron configuration, right? And you put that into brackets, and then you just add the extra stuff to get to the element you're trying to do. So, for example, let's use sodium, for example, right? Sodium is using neons, right? Electron configuration right there, and then it has 1 extra than neon, which makes sense because neon is 1 electron less than than sodium is, right? So let's go back real quick to this slide right here. Right here's neon right there, right? So there's neon right there, and so neon's electron configuration, and it's a noble gas, so everything is full, and that's what noble gas is like. They like to have full shells of electrons, right? And so 2s 1s2 2s2 right there, right? 2p6 because there's 6 electrons that can fit in the p orbitals, right? 2 per orbital, right? And so that's what the electron configuration is for that, right? That's the electron configuration for neon, right? 1s2, 2s2, 2p6. Well, we'll go down one level and now one extra electron for sodium, and you notice it's exactly the same, right? This part is exactly the same, but then the one part that's different is just one extra 3s1 because that's sodium. Sodium has one extra electron than neon does. So why waste the time and write out 1s2, 2s2, 3p6 when you can just say, oh, everything's the same with neon up until the 3s1 part. So we'll just put neon in brackets and say it's all the same as that, neon's electron configuration, and then we'll add in the part that's different, which is the extra electron from sodium, right? And so that's why you see here the condensed is neon in brackets and then 3s1, right? Same, you can do it for the whole periodic table, man. So here's potassium, right? Everything the same as argon all the way up until the 4s1, right? Here's rubidium, everything the same as krypton all the way up until the 5s1. Cesium, same as xenon, all the way up until the 6s1, right? So that's the condensed electron configuration. Okay. So transition metals are a little bit different, and the reason why is because the transition metals go all the way up into the d orbitals, right? And so we have here. Let's just. I'm not going to ask you a lot of transition metals, but just so you know, right? Here is the for manganese, right? And manganese is a transition metal. It's in the D block, right? And so it has a lot of electrons. I can't remember what manganese's electron number of electrons is, but I will make myself go away so you can actually see. There we go. Right. So argon. So manganese's electron configuration is exactly the same as its nearest noble gas, which is argon. Right. Previous noble gas, which is argon. Except that it also has, and so you can actually write it out here like that, argon, right? Because in the brackets, it's the same as argon. But then you have to actually indicate the stuff that's different. And so here we have the 4s2, that's completely full, right? And then it actually has 5, right? It actually has 5 or electrons in the 3d orbitals. See, so 1, 2, 3, 4, 5, right? And so there are 5. Remember how there are only 3 p orbitals, right? From the m sub l, right? Well, there are only 5 d orbitals, right, from the m sub l. And so if we go down to zinc here, which has 5 extra electrons than manganese, right? And again, this is a shortcut way. You can just put AR there, and that kind of gives you don't have to go through and write the entire electron configuration for all of argon, and then do zinc, right? But so if we use zinc here as our example right here, it has 5 extra electrons than manganese does, and so again you fill them up, but you always go through and you fill up one at a time first, right? And then you come back and add in these extra ones right here to accommodate all the electrons in the d orbital of zinc, right? So again, always for always go in the if it's a degenerate orbital, always go one at a time first, and then come back and fill in the rest if you need to with 2 electrons. Okay. And I think that I have one slide about the lanthanides and the actinides, things like plutonium and uranium and stuff like that. I'm actually not going to test you on that at all because I don't do anything with those elements, and I'm not going to make you do any f orbitals for your electron configurations and stuff. So don't even worry about the lanthanides, the actinides, and the lanthanides and the actinides. See, I can't even say it right. I don't even know who studies these things, like nuclear chemists maybe. The chemists that like to create new atoms, they study the lanthanides and the actinides, but I don't do that. So we don't have to worry about that kind of stuff. Okay. So I already talked about this a few moments ago, but if you remember me talking about this, but the different parts of the periodic table actually denote what the type of orbital that you have as your valence electron, right? And so, I kind of drew this out kind of rudimentarily for you a few slides ago, but notice here, all right, we have s orbitals, and the s orbitals are all here in this thing called the s block, right? And we have also one s block element over here. Really, this thing should be drawn over there, right? Because helium is definitely an s block element. It only has 2 electrons, so it only can go up to s orbital. It can't ever go up to p orbital, so there's no reason why you have helium over there. But a lot of people put helium over there because it's a noble gas, right? It's got a full shell, so I guess that trumps it. And then, of course, over here, this pink block over here of the periodic table is the the p block. Sorry, the p block where the p orbitals are, right? And then here's the d block with the transition metals, right here. And then the F block right here. If you ever wondered why the F block is, they always have it where, like, if you have a periodic table, they always like draw it with an arrow, and then the F block goes down here, right? Well, that's because if they ever put the F block, up here like it's supposed to be, it will just make the periodic table way too long, right? So your valence electrons will be the electrons that are denoted by the orbital that they're in from the different blocks they're in, like the S block, the P block, the D block, or the F block, right? See, so yeah, so for example, like helium's valence electrons are it's already a full valence shell anyway, so that's it's got 2 in the s orbital, right, and that's why it's an s block, right? Sodium, I guess let's do sodium. Sodium's right here in the 3s right there, right? Its final electron in its valence shell is in the 3s orbital, right? And so that's why it's in the s block. And then or it's not that's not the reason why it's in the S block, but the periodic table is organized that way so that it would be easy to figure out what block or what orbitals the valence electrons will be. So, for example, if we come over here, there's what is this? Okay, I think this is oxygen right here, right? So that should be boron, carbon, nitrogen, oxygen, right? So here's oxygen right here, right? And its valence electrons are in the p block, right? It's in the p orbitals, okay? And so, and we'll talk about some other like more advanced things later during the chemical bonding chapter, but that's really all you need to know here. The one thing that I do want to take note of here is that remember how I told you that these right here, the principal quantum numbers, tell you the level that the electron or the rho is, what the n equals numbers or the energy level. So for most elements, right, or for most of the representative elements, the period or the rho number tells you like when you say like 4 p3, right? That 4 there definitely means this row right here, right? The 4th row. The only time it goes a little different is when we talk about the transition metals, and I'll show you that in a second when you do you do an electron configuration for a transition metal, right? And I'm sorry, I don't have the transition metals memorized or where they're located, all right? But they are actually one n level lower, right? So where everything on the period 4 or row 4 for the S block is still at the n equals 4, like that one right there, for 4s, or 4p right there, right? Those are all still n equals 4 energy level. But for the d orbitals, right, it actually goes down 1, where it's at 3, of the n equals 3 number, right? So where you had where you had rows 4, 5, 6, and 7 for both the S block and the P block. for the for the D block, though, you're going to have rows 3, 4, 5, and 6. There's going to be one less, right? And that's just because for the D block only, right? For the D block only, and that's the only one you need to worry about. For the D block, the n equals number is actually -1, right? So n for the D block is equal to n minus 1, right? So if it's if you're looking for, like, say, the n number for the first row, right, or the fourth row for the D block, it's actually be n minus 1, which is 3, right? So just keep that in mind when you're writing your electron configurations. And again, I don't have these memorized, so I'm just gonna pick one here, maybe. There are 10 electrons here, by the way, right? That's 10 electrons for the D block, right? Which is different from here, because here it's like there we go. It's 6 electrons, right, for the P block, and then it's also then 2 electrons to fill up for the S block, right? So I'll just pick one. I'll just pick an element here. I don't know what it is. Actually, maybe I should pick palladium, because palladium's so far away. As a chemist, you think I'd have a periodic table like just laying around somewhere, but I don't have a periodic table laying around somewhere. So I'm just gonna pick one. Okay, well, let's just pick this guy right here. I'm gonna change. No, I'm not gonna change pins. Let's say I pick this guy right there. Okay, right, that guy right there. So what would be the electron configuration for whatever element this is right here? Okay, what would be the electron configuration for that? Well, you always got to start at the beginning, right? You're going to do a full one. If you're not doing a full one, you do like a condensed one. I'll show you the condensed one in a minute, but the full one, right? It's going to be you filled out the 2 electrons there and the 2 electrons there, right? So this guy here, my X right there, its electron configuration starts out with 2s2, right? No, not 2s2. I apologize. I skipped a whole n. 1 there we go. 1s2, right, which is this guy right here. I don't want to mark all over it because I'll just get confused, but this guy right here and this guy here, right? And then this guy right here too they're full too, right? So 2s2, right? And then we'll move over to the P block. 1, 2, 3, 4, 5, 6, right there, right? And so this would be, we're on the second row right here, right? So that would be 2p6, because all the electrons in that row are filled for the p orbital, right? And then we'll come back around again to the number 3 right there. So 3s2, because those are all full. And then we'll go over here to the next of the P block right there, which is this guy right here. That's going to be 3p6, right there. And then we'll come back around over here to the 4th row right there. 4s2. There we go. And now this is where it gets a little tricky, because remember I just said that for the transition metals, your n is actually going to be 1 minus that. And so we have 1, 2, 3, 4 electrons right there for that, whatever the element is right there. And so it's actually going to go 3d4, right? Because for the d orbitals alone by themselves, right? Just the d orbitals, their n number is 1 minus the n, right? And so that's why we do D3D4 and not 4D4 like we would do for the actual row number. Those transition metals are such a pain in the butt, right? And I wish I could tell you what this element is. Oh, you know what? I have a periodic table right here. I have a textbook. Let me see here. So here's my here we go, periodic table. And so whatever this one is, oh, how fun. The one I picked was chromium, right? So that's Cr right there. That's the electron configuration for Cr. Nice, right? And so let's see here. And so this is the expanded electron configuration. If I wanted to do the condensed electron configuration, right, I can just go back to the nearest the nearest noble gas. And the nearest noble gas is actually going to be, let's go back, and then go to the third row. And the nearest noble gas is argon, right? So the condensed version of this would just take all that stuff out, and all it would be is argon in in the brackets, right? And then just this row right here that doesn't include the argon, which is 4s2 3d4. 4s2 3d4. See? Let's try one more. Yeah, I can do palladium. So palladium is which one here? It's in the 10th one. So 1, 2, 3, 4, 5. Wait, not the 10th one. Yeah, it's in period 10. So 5, 6. Wait, I'm miscounting something here. Oh, sorry. This is the thing that really gets me sometimes. Like when there's two types of periodic tables, right? There's one where you have it as, A, 1A, 2A, right? 3A, 4A, 5A, 6A, and that tells you the valence number. But then there's other periodic tables that just go 1 through whatever without the A's and the B's. And the B's are usually for are usually for the transition metals. And so this particular periodic table I'm looking at in my textbook right here actually has it where it's both, and so I'm reading the wrong line. So it's actually in row 8. Group 8 right here. So it's group 8, and let's see. How many down is it? Right here. This is it right here. That right there. That's palladium. PD for palladium. So I'll do palladium. I'm doing palladium because it's actually kind of special to me. I met a very famous scientist. He won the Nobel Prize in Chemistry back in 2010 for using palladium as a catalyst to make new carbon-carbon bonds, which was a huge deal. Okay, so let's do the electron configuration for palladium now. And so let's go over here. Okay, and so we'll do the full one verse first, and then we'll do the full one first, and then we'll do the condensed version. Okay. So again, we'll go through the top one first, right? So for PD, its electron configuration is 1s2, 2s2, right? So that's the first row already. The first row plus the second row is s orbitals, and then we'll do the 3p orbitals, right? So that's 3p6, right? So that's all those guys right there, right? And then we'll come back around again to the 3s orbitals, so 3s2, and then 3p orbitals, right? 3p6, right? And I'm running out of room, so I'm going to have to go down one, right? And then after the 3p6, we go back here to the 4s orbital, 4s2, right? And we've run into the transition metals, right? And so again, remember the end for the transition metals is actually n minus 1. And so it's a 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that is going to be 3d10, right? And then what's after 3d10? We're back to 4, right? N equals 4. So that's 4p6. Right, that's 4p6. And then we come back around again to the fifth row right here. That's 5s2. Oh, dang it, we're back down to the transition metal, so we have to go the n-1 route again, so that's 4. And then 1, 2, 3, 4, 5, 6, 7, 8. That's 8. So that's 3d8. Right? And so that's the electron configuration there for palladium. And I ran out of room, so I kind of had to stack them, but you should really write them all out in a single line, right? And if I wanted to do the electron configuration condensed version, the condensed version of this electron configuration the condensed version electron configuration for the I lost my train of thought. For palladium, that's it. The condensed version for palladium, the nearest periodic table before it was this one here, right? So what's after argon? Is it krypton or is it xenon? I think it might be krypton. I never see. I don't have the periodic table memorized. I should probably. I was right. It's krypton, right? So if I want to do the condensed version would just be krypton inside of a brackets, and then the part that doesn't include krypton, which is everything from here and all the way to here. So that would be 5s2, and then 3. Oh, not 3. Did I say 3 here? I did that wrong. I'm sorry. This should be 4. 4d8. There we go. Because I already did 3 up there. I don't know how I did 3 twice. That's my bad. So it should be, this one should also be 4. So, you know what? I'm just going to erase it. Because it's going to confuse you. I don't want to confuse you. This is already confusing, right? Let me see here. Erase. I didn't mean to do that. I hope that I hope you're able to get all that down. What's a video, so you can just pause it, right? So let's just do that one more time. We'll do palladium one more time, okay? Maybe that's what I should have done to begin with. So palladium is where I lost where it was. I think it's right here. So there's palladium, right? So if I want to do the electron configuration for palladium, right, it would be for PD, okay? It's electron configuration. I'm going to do the whole thing again, okay? So 1s2, right? 2s2, right? So that represents 1s2 right there. I mean, that's just the whole thing. I really wish they would just move this guy over here, right? The helium should really be right there, but whatever. And then 2s2, that takes care of those. And then 2p6, right? And then we start back over on this row here, so we're on 3 now. 3s2. And then next row on the P block is that one. So that's 1, 2, 3, 4, 5, 6. That's 3p6. Okay. So we'll wrap back around again to the 4th row right here. That's 4s2. That takes care of that. And then, we're on the D block now, right? So remember, it's always the N for the D block, right? For the D block, the N equals N minus 1. And so here we'll start, even though we have 4 here, the D block's going to start with 3. 3d10, right? Because we take care of all these 10 electrons right here to get to, on our way to getting to palladium. And then we jump back up to the N equals 4 right there for the 4 P's. The 4p orbital right there, p46, right? We'll come back around again to the 5th period, or the 5th row. So that's 5s2, right? And then here we are. We're in the same row now as palladium, but again, it's a D block, right? So it's n minus 1, so it's going to be 4 instead of 5, right? So 1, 2, 3, 4, 5, 6. Wait, did I miscount? 1, 2, 3, 4, 5, 6, 7. There, 7, 8. So 8 electrons gets you to right there where palladium is. So that's going to be 4d8, right, for palladium. That's the full electron configuration for palladium. Okay. And so, sorry, that should be an S right there. It doesn't look like an S to me, but it's an S. Let me fix it real quick because it looks a little bit weird. Excuse me. Looks like a 5. There we go. So now if I want to do a condensed version, right, all I have to do is go to the nearest noble gas that's ahead of it, which is that one. That's krypton. Forgot the P in krypton, right? And so all you have to do then is, if you want to do that, all you have to do then is, for the condensed electron configuration, is say that it's all the same as krypton up to the 5s2, right? So you say that by saying Kr in brackets, and then you put in what's left over. And I don't know why I keep on writing these like things here that shouldn't be here. Oops. I'm still in the eraser. My bad. So 5s2, 4d8. And so that's how you do the electron configuration for both condensed and expanded for palladium, right? But they're all the same thing, right? If I ask you for any kind of electron configuration, they're all done the same way. The only thing that you got to remember though is that you have anything then the D block right there, that the n will not be equal to n. The n has to be equal to n minus 1 for the D block, but just for the D block elements. Okay. All right. So let's keep on going here. So there are a few anomalies, right, in the periodic table. Some irregularities that occur when there are enough electrons to fill half shells of the s and the d orbitals in a given row. One of those is chromium, right? Interestingly enough, chromium, for some reason, should be the electron configuration for chromium here should actually be 4s2 3d4, but for some reason, right, one of these electrons here likes to jump orbitals, right, and so now its actual configuration is 4s1 3d5, right, and it's not some reason. There's a real reason, and the real reason is that because the 4s energy levels and the 3d energy levels are actually very close to each other, so electrons can actually occupy either one. And so I guess for chromium, all right, the actual electron configuration is actually 4s1 3d5, which is interesting because I can't check now because I accidentally erased it, but I did chromium as an example a few minutes ago, right, before I erased the board, and I'm pretty sure I put this as the answer, 4s2 3d4, right, but chromium just, luckily is the anomaly here, right, where it has one electron that jumps to the d orbital, so its actual configuration is 4s1 3d5. So yeah, I forgot about that. So there you go. And there's also a whole bunch of anomalies in the F block, but I'm not going to give you any kind of problems from the F block, so don't even worry about that. Right? Don't even worry about that. And so this takes us to talking about periodic trends and the atomic number. And so we'll talk about this now in the next the lecture. So I will see you in the third video.